good morning everyone. First of all, I'd like to say thank you for having me. I appreciate the opportunity. And so just quickly, my name is Callum, Mackay, and today I'll be talking to you a little bit about some research I've been doing at the University of Northampton, where I've been looking at the role of chrome tanning, the role of water in chrome tanning, and the implications that has on low water processing. And so, first though, I'd like to take a second just to tell you about how the research has come about. So, that is through a knowledge transfer partnership. So what a knowledge transfer partnership is essentially an initiative run by Innovate UK, which is an arm of the UK government, with the purpose of bringing businesses and universities together to carry out research in order to drive innovation in a given field. So in my case, I'm working at the University of Northampton in conjunction with Qualys, which is a subsidiary of the Xeros Technology Group, and I'm carrying out research there where I'm looking at the limits of what the Xeros' X-Source can do in leather processing. So there we go. So the aim of the research is pretty straightforward, and that was to determine the limits to water reduction that can be achieved through use of polymer spheres, X-Sorbs, in the chrome tanning process. So essentially, how little float water can we use when tanning with X-Sorbs without having to, while still producing good quality wet blue. And so in order to answer that question, we've got to attempt to define the role that water plays in the chrome tanning process. And just if anyone's unaware of what X-Sorbs are, what they look like, I've got a bag with me, so grab me at any point and I'll be happy to show you. So we've attempted to answer that question. So we've divided the role of water into 4 distinct categories. So one is its role as a solvent, so it has to dissolve the reagents you've introduced into the drum, so your chrome powder, your basifying agents, essentially whatever you need to use in that as a part of that process has to be dissolved so that they're mobile and able to react with the substrate. Following that, it acts as a delivery system, so through diffusion and the tumbling action of the drum, it brings the dissolved reagents into contact with the pelt and then facilitates their penetration through deep into the fibre structure. Once the reagents are in place, the water provides a medium where the necessary reactions can take place. So in the case of chrome tanning, it allows the chrome to react with the carboxyl groups of the collagen and then tan hide. So on top of these, there are mechanical actions that it provides that are critical in a successful tanning process. So one thing it does is it increases the weight on the hides that are dropping from the drum. So that creates a greater hit pressure when the hide's full, and then that increased hit pressure helps with the penetration of the reagents into the leather. Another thing it does is it provides lubrication, so that prevents excessive friction from being put onto the hide, and then that could possibly lead to damage of the hide, so you might get looseness as a result of that, which obviously you wouldn't want. And then another thing that it does is it separates the hide, so it stops them from becoming entangled together, and obviously if that were to happen, that would ruin the process because you've got a ball of hide that the chrome can't reach the middle of, so you've got a big untanned wad of hide in the middle of the drum. And then on top of all of those things listed, it also helps to reduce the strain on the drum motor, so that it does that by reducing the effect of the dead weight of the hide at the bottom of the drum and the force that the motor needs to give in order to overcome that. So going forward with these functions in mind, we can talk a little bit about the processing of using low float and the implications of that. So at this point, I think it'd probably be a good idea to just define the types of water that I'll talk about. So you've got bound water, so that's the water that's bound to the structure of the fibres, and you can't get rid of that without actually damaging the structure of the leather itself. You've then got the bulk water, which is the water that's in the leather, that's mobile, but that's not integral to the fibre structure. And then you've got the flow water, which obviously is the percentage of water that you'll add to the drum. I'm sure everyone knows this. And there was a study done in 2015 where they looked at the minimum quantity of bulk water that you need in order for the tanning reaction to take place. And so in that study, they used freeze drying in order to remove bulk water from the hide, which they then subsequently chrome tanned. And in that study, they found that just 55% bulk water was enough to allow the tanning reaction to take place. meaning that the bulk water that's in a hydrated hide, so a hide that's just come from washing or a hide that's come from any other stage in the processing chain, should have more than enough water in it to enable the tanning reaction to occur. And yet, there should, so taking that into consideration, there should be no reason why we can't tan without any addition of float water whatsoever. And yet, conventional practice is to tan using anywhere from 50 to 150% float. I know there'll be exceptions to that, but as a general rule. And so why is that? There must be a reason, and there is. So it's because if you were to tan with zero float, you might start to see issues with the outcomes of the process. And that's because by removing the float water, you take away the functions it performs as a delivery system and also the mechanical action that it provides. So you might see things like non-uniformity because there's nothing to aid in the distribution of the chemicals around the drum. You might get hide tangling, again, because there's less lubrication to help that, to prevent that from happening. You might get excessive friction, again, leading to looseness or something like that, which obviously you wouldn't want. And then you could also damage the drum motor because there's nothing to aid with the momentum of moving the drum when you initially want to get it moving. But by introducing Xorbs, what you're doing is you're introducing something that's able to replicate water's functions as a delivery system and also the mechanical action that it provides. So in doing that, you prevent the issues that you see with tanning without float water. And in fact, Xorbs may actually be able to enhance the mechanical action provided compared to water, because with water, as I said, it aids with the mechanical action by increasing the weight dropping from the top of the top of the drum to the bottom of the drum. Xorbs do this, but they also work their way into the folds of the leather and give additional mechanical action where they effectively massage the reagents into the hide, which, as you can imagine, is likely to improve penetration and may improve the distribution as well. And so, going forward, with the idea in mind that we will be able to perform these functions using Xorbs, our aim is to reduce the water usage as much as possible. And since we know that bulk water is enough to tan with chemically, we decided to take away float water entirely, at which point we thought that we may as well take it one step further and bypass the pickling stage and its associated inputs. So our aim was to be able to start the process at a pH close to what you'd see at the end of baiting. So instead of starting the process at a low pH to enable penetration to happen, followed by increasing the pH to fix, our intention was to start at a high pH, and in doing so allow penetration and fixation to occur in parallel in a similar manner to the three-brew process by the dozen time. And then one thing is to note when you're taking this approach is that you run the risk of not being able to achieve full penetration because of the increased reactivity of the system apparent when you're tanning at a high pH. So our tactic with the trials was to start them with a relatively open substrate. So we started using sheepskin, and then just to test the chemistry of the reaction, see whether it worked, and then before adding too much of a penetration barrier. And then after that, we progressively increased the barrier to penetration by moving to thicker, less open substrates. So we moved onto split hide and then full thickness hide. And so in the sheepskin trials, we started off using a pH 7, 8, and 9 as a starting point for the process. And then we used those results to tailor the starting pH of the subsequent trials. And then we took all of them into consideration and then used the best results that we got to tailor the conditions for a pilot scale trial, because we wanted to see how well the process fared when it was scaled up. So moving on to the sheepskin trials here, I was a bit worried that you wouldn't be able to see those bars, so I'm glad for that. So in this trial we used 3 1.5mm sides, sheepskin sides, in a small dose drum for each trial, and we measured the time to full penetration, the final pH, the colour uniformity across the surface and through the cross section, and also the shrinkage temperature of the resultant wet blue. And what we found that was in all cases, so all of the starting pHs, we produced good quality wet blue all around. So all had uniformly high shrinkage temperatures. So for the pH 7 trial, it was 109 degrees, and for both the pH 8 and pH 9 trial, we got 111 degrees, which we were happy with. And all of them were uniformly coloured, both across the grain and through the cross section. One thing that we saw is that the final pH finished below what you'd want at the end of a tanning process. So usually you'd expect it to be around about 4, but it was below 3 in all cases. But as you can see from the results that we got, that evidently didn't have a detrimental effect on the TAN reaction. The penetration times at the bottom here show actually quite nicely how the penetration barrier is increased when you increase the starting pH. So as you can see, at pH 7, it's 1 hour, it's 1 hour to penetrate fully, pH 8, 1.5 hours, and pH 9 to 2 hours. And that quite nicely pushes home the notion that as you increase the pH, you increase the reactivity of the system, therefore the chrome finds it harder to penetrate all the way through the substrate. So with those results in the bag, we felt pretty confident moving on to split hide, which comes with a greater intrinsic barrier to penetration, and obviously we were using a thicker substrate as well, so that should make it a bit harder. And in these set of trials, we just used one split hide because it's larger, you don't need to add as many. And we also tested only at a starting pH of 8 and 9, and the reason for that was twofold. So one was that we demonstrated already that pH 7, pH 8 and pH 9 work in sheepskin, and we've also shown that the penetration barrier is increased when you increase pH. So we can pretty safely say that if we can get it to work in split hide at pH 8, it should also work at pH 7. And then the second reason was that the intention was that this process could be carried out directly after baiting, and it's pretty unlikely that the pH would be all the way down to 7 immediately following baiting. So because of those reasons, we didn't test with pH 7 in these trials. And what we found from these trials was that by starting at pH 8, you produce good quality wet blue on par with what you saw in the sheepskin trials. So again, uniformly high shrinkage temperatures of 113 and uniformly coloured wet blue across and through the cross section. We actually got full penetration in the same amount of time it took in the sheepskin trials at pH 8, so at the same pH. And again, we ended up at a lower than optimal pH, so we were at 3.15 at the end. Again, no issues as a result of that, so it's not a problem. But when we started at pH 9, that was a much different story. And that's because the increased pH in combination with the thicker and harder to penetrate substrate prevented the chrome from being able to penetrate all the way through the cross section. So what we saw was that a hide that had been tanned on the outskirts, but that had a thick untanned layer through the middle of it where the chrome hadn't been able to penetrate through. And so you can see on the thermogram on the right, the bottom line is something along the lines of what it should look like, and that's the line that we got for the pH 8 trial. Whereas at the top line is what we got where we started at pH 9, and as you can see, that all over the place, and that's because the shrinkage temperature was all over the place because it hadn't managed to penetrate all the way through. And then again, if we look at the final pH of the pH 9 trial, so down there at the bottom, you can see that that's above what you'd really want for the end point of a chrome tanning process. So it just kind of drives home the notion that the system was too reactive to allow the chrome to penetrate all the way through. So using these results, we then went forward to a full thickness hide using just pH 8 as a process starting point, because realistically, if we can't get pH 9 to work in a split hide, there's no chance it will work in a full thickness hide. So in these trials, again, just one, we used pH 8, and we used one side per trial, one 5 mil side per trial. And what we found was that when we started at pH 8, we got a relatively high shrinkage temperature of 108, but it wasn't uniform by any stretch of the imagination. And the colour through the cross section was also non-uniform, so there were parts that were more tanned than others. And as you can imagine, it took a much longer time to penetrate compared to the previous substrates that we were using. So it's at some point between 8 and 16 hours, and that's because the pH was much more reactive. It was a much higher pH, therefore it took a lot longer to penetrate through a thicker substrate. And that's likely a reason why we saw the variance in shrinkage temperature, because there may have been some areas where the chrome penetrated earlier, so there's some areas with a higher chrome content and therefore a higher shrinkage temperature, and other areas where it couldn't penetrate as early, had a much lower shrinkage temperature. And so in order to combat this, we ran another trial in which we added 0.5% formic acid alongside the chrome, so we added them at the same time in the hopes that that would reduce the reactivity of the system as it penetrated alongside the chrome, and then allow the chrome penetration to happen earlier, therefore getting a more uniform shrinkage temperature. And that's exactly what it did. So it brought down the pH and allowed the chrome to penetrate in just 7 hours compared to the 8 to 16 hours of the previous trial, and produced a really uniform shrinkage temperature of 104 degrees, which I thought was a good result and really promising. However, we wanted to get a higher shrinkage temperature ideally at the end of this process. So we were looking for something along the lines of 110 degrees and above. And so we didn't take this process through to the pilot scale trial. Instead, we took the split hide trial that we used at a starting point of pH 8. And so these are the results we got for that. So like I said, we used a pH 8 as a starting point in split hides at 2.5 mil. And what we found was that, like in the small scale trials, we produced good quality wet blue with a uniform shrinkage temperature and uniform coloration throughout. And what we also found was the process became more efficient as it was scaled up. So we achieved full penetration in just 30 minutes as opposed to the 1.5 hours that it took in the small scale, which can be explained, I think, by the greater weight in the drum aiding with the penetration. And then also, what I think is a more significant result, we achieved well-tanned, so uniformly tanned wet blue with a shrinkage temperature of 112 degrees after just 4 hours of tanning, which rose to 113 at 6 hours and 114 at 8 hours, which was the end of the process. And then as a final check, we crusted the wet blue just to see how it would fare in subsequent processing steps, and what that showed us was that we produced good quality wet blue that fared well in subsequent processing steps, so it was all good. And these are a couple of pictures, I'm not sure how well you can see them on the screen. So the left-hand picture there is the wet blue that we produced in that pilot scale trial. So it's, I think it looks a bit darker on the screen than it does in real life, but it's a nice light blue wet blue that's uniform across, and there were no complaints there. And then on the right is the crust leather that we produced. So as you can see, no looseness, no issues with the grain, no complaints. So what conclusions can we make following the trials that we carried out? So from the sheepskin trials, we can say that Exorbs, we are able to relatively easily tan with zero float and overcome the penetration issues associated with tanning at pH 7, pH 8 and pH 9. From the split hide trials, we can say that whilst Exorbs aren't able to overcome the penetration barrier at pH 9 in a less open substrate, they are able to tan effectively with zero float at a starting pH of 8 in split hide. And then from the full thickness trials, what the results have shown us is that it is possible to use Exorbs to force penetration of chrome through a thick substrate at a high pH, but the process does need some level of tweaking in order to get the shrinkage temperature that we want and the uniformity that we want. And then finally, the pilot scale trials just demonstrate that the process is definitely scalable, and in fact that the process becomes much more efficient when it is scaled up, which I think bodes well for the future possibilities of a full thickness process working, because obviously if that was more effective when it was scaled up, hopefully we may see more success with a full thickness process. So, final slide, what are the implications of the conclusions that we've just made? So what we can say is that through use of a pickle-free, float-free chrome tanning process using Exorbs, tanners may be able to reduce water consumption because you're not using any float water in the tanning process. May be able to reduce chemical consumption because there's no need to introduce bases to bring the pH up at the end of tanning, and also because you're entirely removing the pickling step and the associated salt and acid inputs. You may be able to reduce processing time because you can bypass the pickling step, obviously, and you also may be able to reduce the tanning time of the tanning process in line with what we saw in the pilot scale trial. Effluent output, again, because of the reduced chemical input, and also you've got a reduced quantity of contaminated water at the end of the process. And then also energy consumption, because there's a reduction in the processing time, therefore you won't be using the drencher as well. And you can do that whilst producing high quality wet blue with no defects whatsoever. And I'd just like to thank everyone that I've been working with on this. So Tony Coverton, Will Wise, Alice Dookie, Full Servant and Karen Hussain. And thank you very much for listening.